Bismillah ar-Rahman ar-Rahim. Welcome back to our second part of our course, Deep Learning for Computer Vision. Today, we are going to start with the next part of this course. We'll talk about, as a starting step, about the neural networks, about the machine learning, and we'll try to cover in general and in some specific details many of the topics regarding these techniques and algorithms. And I hope that you'll enjoy it in this lecture and in the coming also lectures regarding this topic. So let's jump to our first lecture. It will be entitled as Introduction to Artificial Neural Networks. And let's jump and see it and go to the details regarding this topic. So as you see here, the lecture number 11 will be about, it will be concerning the introduction to artificial neural networks, ANNs. The decision guidelines will be as see here. We'll start with warming up with the ANNs. We'll talk about some key terms of ANNs. We'll discuss the main type of ANNs. We call it the feed-forward ANN technology or topology. We'll talk about also the convolutional ANNs, CNN. And we'll discuss also the recurrent NNs, shortly RNNs. As a start, if you remember, we discussed this issue in the first few lectures of this course. The artificial intelligence or the computer vision part. Here we'll talk about the what is the artificial neural network, or simply neural network, ANN or just NN. In fact, the NN is an interconnected layers of small units called nodes that perform mathematical operations to detect patterns in data. So the NN in general, to be simplified, it's just a sort of interconnection between small units, we call it layers, and these layers or nodes. And these nodes are going to perform specific mathematical operations, simple mathematical operations, and with a target to get some output. This output will be based on your task. If you are going to provide this network for, let's say, classification of inputs or to detect some patterns in your input data, and in a very wide range of applications, as will be discussed in the forthcoming part of this lecture. Now, the NN algorithms are built in a way that mimics how the human neurons work. What does that mean? Usually, the neural network is a model of the artificial neural network is a model or a sort of modeling of the natural neural network in our human bodies. And we try to mimic and try to interpret and repeat what the human neuron network or neurons are doing in our brains. As was said, it's an in-joke by Deepak Chopra, that your brain does not manufacture thoughts. Your thoughts shape your neural network. This is the main idea behind the neural networks as artificial neural networks in general. So, in fact, the NNs are all hype in machine learning. So we are all machine learning systems and devices are based or built on a basic idea or a basic building unit or block, which is the ANN. In fact, I can say it's a revolution in computer vision that has been made in the last few decades, maybe in the last two or mainly two decades, is attributed to the presence and the implementation of the ANNs. Now, understanding the basics of neural networks will be beneficial by helping you stay engaged in a conversation around this topic. So when you understand and you comprehend the basics of the NNs, you'll be able to mainly understand and build up your knowledge in this field. This is either in machine learning and deep learning and in related topics around this idea. Where we can use an ANS, we can use it in a bunch of applications, in a wide spectrum of applications. You can find it in communication applications like in mobiles, in connections, wireless connections to process or to deal with noisy data, in self-driving cars. You can also find its applications also in natural language processing. We call it shortly NLP, where this may include communication to your voice and to take activations or actions according to your commands. All these things can be done very easily and straightforward or very simply using NNs in general. As a starting step, let's go and see what are the key terms for NNs. If you look at this structure for the neuron, it's a natural neuron. You can see how it is constructed or how it's created. In fact, we are not going to go deep in these details. However, we'll just try to mimic or understand and take advantage of how it works, and we repeat or we try to model something artificial that looks like or comes very close to the operation and the performance and the principle of work of this neuron. If you look here, you can see that this is our model. Here we have the input. Here we have the output. Let's take some here, as you see, that this is these are the inputs coming to the neuron, and this is the output, maybe to the next stage or the next neuron. Similarly, we can model this as having these inputs to the let's say to the model or in the neuron or the artificial neuron. And on the other side, we have the output, as you see here. Okay. Now, what is going on inside the neuron? What are the key terms of these neurons, let's say, or these natural components or organs, let's say, and what we can do in case of trying to model and getting something artificial to repeat or to try to copy what is going on in our human organs or maybe thinking. Let's start with the first step or the first part. We have here the inputs. Here we have the input. This input can be data or values that are passed to the neurons. As see here, we can see this here. These are the area or the regions or of applying the data. Next, we can have the neuron part. Here, the main neural network or neural network building block is the neuron itself. It takes the weighted values from the inputs and applies specific mathematical operations. So we take the inputs from here. We process these inputs in the neuron. Here, the same thing is here. And usually what was going on inside here, we can understand that sort of weighting or applying some sort of balancing of the parameters according to specific weights. We'll talk about this later on. And these calculations and mathematical operations can be done in the neuron. Then after that, we can get the output to the next step in the neuron here, as you can see in our model. Maybe not very clear, but we will discuss this in details. This unit is called, or this neuron is called in unit or node or perceptron. These are the same, have the same meaning. So what is going on next? Now we having this operation being done and operated. So after applying the operation in the neuron, here the same thing is here. We get this result or the output. Will, as in this case we have it as y, and here are the outputs in the natural neuron in our human bodies. So if we go deeper and see what is going on now, as you can see here, we have the inputs, x1, x2. This can be data, it can be image, it can be a sort of maybe codes, etc. will be applied to our neuron part. Here we have to multiply these inputs by weights, W1, W2, W3, etc., up to W, let's say, N. Next, we sum all these weighted values and adds a sort of bias, this bias is used for calibration purposes and to get some sort of balancing of the resulting output. So the weights are now are very important parameters because they represent actually the strength of or the degree of importance of your connection between the neurons. I mean, here we have one neuron will pass our result to the second neuron. We have a series of neurons, or let's say neural network components will be connected to each other to get a series of neural or neurons to perform complicated or maybe complex functions. Next, what we can do also, we have also the base, as I just said. The base here is used as a constant value that is added to the sum in order to get some, let's say, balancing or respective output of this operation. This can be produced as you see here after applying the summation with the balance or with the bias. You can apply to the next step with what we call it here the activation. So what is the activation? It's a sort of function that performs a nonlinear operation. So the function is adds a sort of nonlinearity phenomenon to the produced output after summation of the weighted inputs plus the bias, and this output will be applied to the activation function. The activation function here, as you see in this part here, is performed and is connected to this output in order to get the final step or the output of this neural connection to get finally the output at least at this stage. Now, how we can find this output y hat? It will be as the g function result of the input, which is the x value multiplied by the weights. So the x here, it's a vector, and w is also a vector because we have x1 up to xn. The weights are w1 up to wn with an added bias. And the result after applying the activation function will give you the output, the required output value y hat. So do we have only one type? No, we have a lot of types of ENNs. So what are the main types or the major categories of neural networks or the neurons in general? So there are many classes of NNs. These classes also have subclasses because we can go further and find subcategories of each type of the ANN. Now, in general, the ANN can be obtained by having a hardware implementation or maybe a software or maybe both hardware and plus software. And this variety of topologies and variety of different types of NNs and different types of learning algorithms will produce a wide spectrum of applications that can be adapted to a very big bunch of applications in engineering life, in social life, in any aspect of your life that you want to implement. And it's actually very clear in the last few years, where we can find maybe in this list of applications for the neural networks. The first type, mainly, we can say that it's the feed forward and ends. And the second major type, it is the convolutional and ends, CNNs, where we implement the convolution idea or the concept. And we can also find a main category, which is called the recurrent NN. It's the RNN shortly. So let's go and span and dive deeper in these definitions and these types and categories of NNs. You can find good information in this YouTube link. You can open it and have some time to see. It's very interesting, actually. Let's start with the first type, which is the feed forward ANN. Now, the FFANN shortly is an ANN where connections between units, or as we just classified or described this, the unit can be the neuron itself, or the perceptron, or the unit itself. So in the FFANN, the connections are made between these units, and there's no feedback, or there's no cycle or loop. So you start from the input and go to the output with no information about what's going on in this system. So you get the output regardless, and you don't have any feedback or cycle or loop to go back and correct your output. Here, the information, as I've just said, it moves forward only in the forward direction from the input nodes throughout the hidden nodes. Of course, in the big or in deep neural networks, we have a lot of neurons or a lot of nodes or layers. And here we may have some hidden layers or hidden nodes. If sometimes you do not usually you don't have, it's not a must to have a hidden layer. Sometimes you may not have any hidden node, or in this case, you just need to pass from the input through the perceptrons to the output. So there is no feedback, there is no backward direction from the output nodes to the input nodes in this case. We can recognize two types of perceptrons in this case. We call the first type as, see here, it's the single layer perceptron, SLP. The second type, of course, we don't have just only single. We may provide a lot of, let's say, perceptrons, and we get what we call it the multi-layer perceptron, MLP. These types are usually used in all systems in case of applying different neural networks and their applications. Let's start with the simplest case. We have the single layer perceptron, SLP. Here, it's a very, very simple model where we have only one perceptron, one layer or single layer perceptron. And the system in this case doesn't contain any hidden layers. So it consists only of a single layer of output nodes. So this is the model of our perceptron. As you see here, we have the inputs. We have the inputs here. Here we have A1, we have A2, A3, etc. up to AN. It's the same thing as X in the previous slide. Here we multiply every input by a specific representative weight from W1 to Wn. We apply summation here. We add some bias. Okay. Then we pass this to the activation function. In this case, our activation function is denoted as sigma, from the word sigmoid, maybe, because it's very common in neural networks to have sigmoid activation function, as will be seen in future lectures and slides. So here we have the input data is as A1, A2 up to AN. The weights are, corresponding weights are W1 up to WN. B is the bias. We have only one bias in this case, and sigma is the activation function, and the output Y will be, as you see here in this equation, Y equals the activation function of the variable that has been produced output as the output of the summation plus the bias of the weighted inputs plus, of course, adding the bias to get the output Y. On the contrary, when we have the multi-layer perceptron, here we have not only one single layer perceptron, we have many, maybe two or more perceptrons in this case. So in MLP, the neural network, it has at least three layers. The input layer, we usually do not consider the input layer as a part, let's say, we do not count it in our, when we count the number of layers, we do not include the input layer as the first layer. It's the zero layer. We may have some hidden layers, additional layers, and the output layer. Now, each layer operates on the outputs of the previous layer. So when we have successive perceptrons, we can see that the output of the first layer will be applied to the second layer as an input for the second layer, and so forth until we reach the final layer in our neural network. Good example here, we have the inputs. As you here, we have the inputs. This is input 1, let's say A1 or X1, 2, etc. Maybe in this case, we have just 3 inputs. Now, the input layer here we have where we multiply and add biases, the weighted sum of inputs plus the bias. Then each node here is connected to all nodes in the next layer. This is the main, let's say, construction of the MLP. Now, in this case, you can see that this layer has been added to this part. So it is an added hidden layer. Usually, we do not care, or let's say, we not go deep in finding the main idea behind using the hidden layer is to add more complexity to our system in order to get to solve more complex, let's say, tasks. So in the hidden layer, the operation is the same. So we repeat. This is in this perceptron, we repeat the same process as in this one, where we have the inputs coming from all these nodes to the hidden layer perceptrons, and this will be repeated with all perceptrons, as you see here. For in this case, we use, let's say, 4 perceptrons to perform or to construct the hidden layer. Now, this number is, of course, is not arbitrary. It can be chosen, let's say, in a specific manner, maybe with a range of number of, we call it number of neurons, or even number of hidden layers, for sure. Finally, the output will be applied, let's say, for this example, to the output layer, where we have here just 2 outputs. Number of outputs is organized by your task and by the problem under consideration that you want to solve using this neural network. This image shows you that we have the sphere, and inside we have many hidden layers. The number of hidden layers is ruled by many parameters and many, let's say, conditions that can be selected, and this will be also uncovered in the next slides and in next lectures. Now, if you look at this statement here, we have done by Lippmann in 1987. As here it states that an MLP with two hidden layers is sufficient for creating classification regions of any desired shape. In fact, this is true, but the classification in this case will not be, nowadays we can have a very large number of hidden layers, and we may go deeper and deeper, which means we can increase the number of hidden layers to a very large number to get very precise and very good or very nice output for classification and maybe for other, let's say, tasks like regression, maybe like object detection. All these things can be found according to the structure of the neural network that you are using and the number of hidden layers and parameters used in this neural network. So the MLP consists of multiple layers of computation units. These units are the perceptrons or the nodes, usually interconnected in a feed-forward way. Again, we have in MLP, we are talking now about the first type of neural networks, which is the feed-forward neural network. And in general, in general case, the MLP is interconnected in a feed-forward way. Of course, it's going to just to mention here that we can apply a back propagation or a back or reward back, let's say, we call it back propagation, in order to correct our output and to get better performance as a feedback to the system. This will be also discussed. Today we are just trying to give some brainstorming about the neural networks types and applications in general. We'll see this in details in later on. This statement is the same as, again, we are, again here we are pressing on the idea that the connection is made in a forward direction from the neurons to the subsequent, from the current, let's say, layer to the subsequent layers in the neural network. In fact, in MLP, usually we use a sigmoid function as an activation function. Now, what about other activation functions? This also will be discussed later. The simplest way is to use the sigmoid, and this is very common in neural networks. Now, in general, MLPs are able to learn nonlinear representations due to the implementation or the usage of or the use of the sigmoid function and the structure that is made by applying the weights to the inputs, adding a bias, repeating this with other neurons or units, and repeating the layers until we reach our desired output for classification, for detection, for regression. It depends on your application and your task. It's a good example in general demo for you to have. Here we have, as you see, here we have inputs at the side. Here we have x1, x2 up to xm in this case. As here we have the notation layer 0. So the input layer is not counted in your neural network. All these layers next to the input are all layers, are again are layers of units or perceptrons, and these layers are considered as hidden layers. So layer 1, layer 2 up to layer L-1 are hidden layers, and finally we have the output layer, which is layer L in this case, and this gives us that this system or this neural network has L layers. The number of layers in this neural network is L layers. So the notation in this case, if you look at let's say these values here in this circle, here we have A subscript J and subscript L small minus 1. This means that the activation function or the output. So the output after activation is also the output of the ith neuron at the nth layer. So we are now at the, if we are talking about the layer here, now we are talking about this, for example, this is the same thing as here. Okay, so this is the activation function. This is the activation function. Okay. Okay, this is the activation function of the nth layer of the neuron I at this layer. Now, if we go to the weights, for example, this weight, let's remove all these things here. If we go to the weights, okay, here the weight WIJL, this is the same thing as here. Here it's the weight of the connection of the jth neuron. This is the neuron J, number J, okay, in the L-1 layer. So coming from L-1 layer, this is the connection, okay, to the neuron I, this is the neuron I, in the layer L, Now, when we go to BL subscript IL, it will be the bias term of the ith neuron, as we see here in this case. Now, we are on layer L, and we have the neuron I, and the bias will be B subscript I subscript L. This sort of notation that can be repeated. You may use other notations or other symbols. However, the main idea is very clear here, as you see in this slide. The second part of, or the second type of the neural networks is the convolutional neural network, CNN. Here, we call it sometimes CNN or sometimes convnets. They are very similar to ordinary MLP, made up of neurons that have learnable weights and biases. The same thing as in case of the neural networks. However, we are using here the term convolution. This topic was inspired by the organization of the visual cortex. In the visual cortex, actually, we use units, or we have units that respond to stimuli in a restricted region of the space known as the receptor field. This is very related closely to the human vision system and how we perceive or the different fields or objects in an image, or maybe in a video, or what we can see in general. These receptor fields are partially overlapping, and they cover all over the entire visual field. So what is the difference here is that instead of having neurons and instead of having, let's say, units, we're going to use convolutional layers. We'll see this in details in the next slide. Now, the unit response in this case can be you can say that if you try to approximate using the nodes or the neurons or neural perceptrons, it will not be very easy to overlap or to cover the functions done by the visual cortex. So the unit's response can be approximated easily or mathematically by having a type or very similar to the conventional operation. So where we can find CNNs, in fact, the list is very long. We can see this in general in image processing and video processing applications. This covers recognition, face detection, natural language processing, automated driving. All these things can be a good candidate for CNN applications. A good example here is the LUNet, one of the first convolutional networks that was produced maybe 20, 30 years ago. Here we have this handwritten digits 2. This is an input image of the size 28 by 28 by 1. grayscale image, handwritten. You can apply this input image to the ConvNet or to the CNN, where we have mainly combination operations, 1, 2, etc., maybe less or more, many combination layers. And there are other supporting functions like max pooling, like the different types of pooling applications. And when you go further and further, you are concentrating on the features and trying to extract these features from the input image, which is in this case the handwritten digit. And after that, you can apply or use the what we call it the fully connected neural network, and get that this output or this two can be detected or classified as two as a final result of your neural network. In this case, of course, we have a CNN or ConvNet. Another example is to have an image at the input. As you see here, we have a car. Sorry. Here we have a car. Okay. This is the car or the image in front of your CNN. You try to apply the convolutional, the intermediate stage, which will be convolutional layers with activation functions, with pooling operations. This will be discussed in details in a separate lecture. And as you move further, you are extracting features, or you learn features from the input. And at the final stages, you can apply the classification where you get this is a car or a truck or a van, etc., or a bicycle. It could be anything else. This is one of the big, let's say, PowerPoints or power advantages of using CNNs. As you go further from the input to the output layer, you are increasing, you are concentrating on the features, and you learn features from this object or from this image. And finally, you apply to the final stages to get at the output a specific class, or you can say that this is a car, or it could be anything else. It could be truck, van, etc. So why CNN is a good where we can find the CNN, where it can find applications. If we start, the main and the very big and heavy application of the CNN is in medical applications, in medical imaging. In this case, you can examine thousands of images or X-rays, maybe, or pathology reports to visually detect the presence or absence of a specific illness or a cancer or tumor in this image without the need for a doctor to see or to decide. It can make decisions, and it can give you specific, precise classification for this type or that type of illness or problems. Also in audio processing, it can be used in key detection. It can be also used in microphone to detect when a certain word or phrase is spoken. As you know, in your mobile phones, mainly in the Android and in Google supported devices, you know Siri that helps if you can ask, and it helps you to find out or to get some result, or to get some search output, etc., for your own according to your own request. Also, it can be used for in object detection applications, in automated driving applications, to detect the signs of the traffic signs, to detect objects surrounding the car or the mobile, the vehicle. All these things can be done and provided and supported by different types of CNNs. A very important also application is what we call synthetic data generation. Maybe I think you may heard about the generative adversarial networks, GANs. The GANs, they are made based on CNNs, and where you can, let's say, if you have a data set of images and you want to produce, you don't have enough images in your data set or database, you can produce new fake images, unreal images that are not similar to any person in the world, and you can produce these things by these images by using the GANs to apply it for deep learning applications, as will be seen later. And it can be also used for detecting fake images or detecting fake, let's say, or operations or actions or decisions, etc. All these things can be done using synthetic data generation. It's a very hot area of research and of applications in the last few years, and I think it will be developing in the next future, in the very few future, in the in few years, and I think it will be very very important in our live applications. The third type of neural networks is the recurrent NNs. What is the difference between this type and the other two types that we discussed before? In RNN, in general, the connections between the units are made in a cycle. So they form a directed cycle. So they can propagate, the information can propagate from the input to the output in forward direction and can be also in the backward direction. Here, from later stages to earlier stages. It's clear that in this case, you may need some internal memory to process specific or arbitrary sequences in your inputs. So it's very important that you may need, so this means that it requires higher computation, it requires more complex systems and with higher processing, let's say, memory facilities. Where we can use RNNs, it can be used in unsegmented, for example, in unsegmented or connected handwritten recognition. So when you write, you may have some connected handwritten text, and in this case, this RNN helps you to do this. You can also apply it in speech recognition. In general, in any sequence processing application, you can find good. You can find it as a good candidate for implementing the RNN networks. Of course, we are not going deep to go deep in describing or explaining the RNNs here. However, if we look at this image, you can see that this is the original or the traditional, or let's say, the feed-forward neural network. And on the other side, we have here the RNN. Very clear from this figure that in the neuron here or in the unit, you may have some feedback or backward connections or arrows where you can get some info from the output and feed it back feed it back to the neuron again and process it again and again. Now, if you look at the neuron, in this case, it contains the original, the classical summation of the weighted sum plus the bias. Also, you can see that you have a time parameter here, that the input at time t minus 1, t plus 1. So we have different time slots, time sequence operation here, and this will be beneficial in finding complicated or complex features and complex, let's say, hidden objects or patterns in your input by using the RNN. There are a lot of types of RNNs. One-to-one, this means that the connection is made here one-to-one. You may have it one-to-many, or many-to-one, or many-to-many. So you may connect all these nodes. Maybe you may connect this way, etc. All these things can be found in RNN topologies and applications. Let's keep things simple and try to avoid complications now, because we are just starting. Let's see now. We have a very simple here an example. Here, suppose that you have this network, you have an input layer. Here the input layer, so layer 0. You have the output layer, and you have in between the hidden layer. So we have one hidden layer here. Here the nodes are denoted as x1 for the input, x2, and the hidden layers are taken also very simply just two neurons, and having only two neurons or 2 units, and the output just 1 unit at the output. And suppose that you are given now why we selected or why we choose these numbers just for demo applications. This is the input x with 2 and 3, so we have x1 as 2 and x2 as 3, a value of 3. The bias is taken by as we set always bias to 0. Okay, the weights here we have W1 as 0 and W2 as 1. Just for demo applications, of course, these numbers are not applicable. Anyway, we can use it just to show the main idea of the simple case of ANN. Here they say the activation function is made as the sigmoid. Sigmoid or sigma of z is 1 over 1 plus e. This is the sigmoid function, the S-like shape function. 1 over 1 plus e times minus z. That will be applied to all these nodes in the system. So this sigmoid or the activation function will be applied to all neurons or all units in our example. And in general case, in all other NNs. So these are our input evidences. And now we want to find out the output O1 in case we have the input 2 and 3. So x1 equals 2, x2 equals 3. We used the color blue for x1 and x2 we used actually in this case the red color, just red font, just for demo purposes. So we have here W1 equals 0, 0. So W1 is related to the input x1 and W2 is related to the input x2. So W1 equals 0 and W2 equals 1. Now we have connections getting out from x1 node to both nodes in the hidden layer. Similarly, from x2 we have two connections. In fact, it's not always the case. Sometimes we may skip some connections. However, we leave this for next lectures. So what we can do next? Now let's see what will happen in the first layer. Again, this is W1 and this is W2. As you see here, we have W1 equals 0 and W2 equals 1. Let's see what will be the output or the activation of H1. H1 will be as a result of applying the activation function, which is the sigmoid in our case, of W x1 plus b. Now we have W1 as you see here, we have x1 equals 2, W1 equals 0, okay? So in this case, we have the value of 2 by 0 plus the value of 3 by 1. So this is the input to H1, and this will be 3. Now the activation function is the sigmoid, so we take this value 3 and replace it in the place of z to get the output. In this case, we have the value of 0.9526 for H1 in this case. Similarly, we can find the output of H2 in the same manner. It looks like that we have almost the same output. Now we continue. This is the value of this place, and this is the value of the same thing is here. Now we need to find O1, the output, having the weights W1 equals 0 and W2 equals 1, having the inputs for O1 from the branch coming from X1 or from H1 is 0.9526, and here the same thing, 0.9526. So what will be the output here? It will be the activation function or the output of the sigmoid after multiplying the input to this node, or the output node. So we have this value multiplied by this value plus this value with the weight multiplied by the activation or the output of H2, and this will be the second part. This will give us something like 0.7216. So this is the output, the final output of this simple neural network in this case. As you hear that what we do here is just to multiply the inputs to each node by the weights and add a bias if there's a bias. In this case, we don't have the bias. The bias is set to 0. In general case, we have some bias value. Then we apply the activation function, in this case, the sigmoid, to get the output of each node. Then we continue and repeat this process until we reach the output of this neural network. Finally, you can go and see these selected links. Actually, you can find a lot of information about, as a starting step, you have YouTube videos. They will be very helpful for you to get some exercise activities to get some good info about as an introduction to the neural networks in general. I think that we are done, and mainly that's all talk. And hope it was very useful for you, and waiting to see you in next lectures. Assalamu alaikum.